Good afternoon and welcome to MAE 209 Probability and Statistics. My name is Richard Kohar and this is lecture 11. And in today's lecture we're going to be covering the expected value and variance of a discrete random variable. Just as a reminder, before I start, there is some skeleton notes that are posted on Moodle. So if you don't want to write out everything that I'm already pre-written, feel free to download that PDF and you can print that off and join along. Just as a reminder though, we have our midterm 1 that is on Thursday. The details are posted online on Moodle, but basically it'll run very similar to quiz 1. It'll be an open book, self-proctored test, and you'll submit a PDF of your solutions through Moodle, and that's how we'll grade them. Okay? So, without further ado, here we go. We'll start talking about the expected value. So the expected value, we can have a definition here. So if x is a discrete random variable, then the expected value is given by this formula. And we'll have to fill in the blank here. So the expected value is equal to the sum over all the possible values that x can be. So it's x times the probability. Now in the textbook, they don't usually use this kind of notation. They're usually writing it like something like this, where they write d, and then they have x times p of x, where d is the set of x values, and p of x is the probability mass function. So, in other words, what the expected value of x is you can think of it as a weighted average of the possible values that the random variable x can take, and each value being weighted by the probability that x assumes. Just as a small remark, instead of using something like with sigma notation where we have a counter variable like x equals 0 to n, we're going to write it usually with the sigma all of x. And the reason because it's not necessary that the x values are consecutive integers. So in the textbook they kind of use like this d likely for domain. For me, I usually, in our course, I'll write out all x, okay? And hopefully that is clear enough. So what we can do now is we can return to our previous example that we did, which was with the bomb strikes in World War II in the south of London. So this was an example that we had done in lecture 10, the last lecture, and we said that let x be the number of bomb strikes in a grid cell, and here is the PMF, or the probability mass function. I have the x values, and then I have the probability values down here, and we're asked to calculate the expected value of x. So what we can do here is the expected value of x is equal to all the possible values of x. So it's x times the probability associated with it. We had also said last time we figured out that this greater than 5 is actually, well, there's only one case where that happened, and so there was just one square that actually had 7 bomb hits. So what we can do is calculate the expected value of x. So that is taking the x value, so we have 0 times its probability plus 1 strike times its associated probability plus 4 plus 7 times its associated probability. Okay. So we can always pull out a calculator for this. So what I have is, this is 0, so we'll have 0. 1 times 3.66. We have 2 times 1.16. We have 3 times 0.061. And lastly, we have it for 7. And so the expected value that we get is 0.933. So what that means is that the expected number of bomb strikes in a grid cell is 0.933, or approximately 1. So that's what we would expect. Moving on, with the expected value, we can also do an expected value of a function. So we don't always have to necessarily have e of x, the expected value of x. We can actually have some function, say h of x, and that is a function of the random variable x, and then we would like to know what the expected value of that is. So very similar to what we do with this, what we have done is replace the x with now h of x, and similarly we're just going to remove basically modify this part right here. So it's not going to be x, but it's going to be h of x. So kind of following our definition, what we had from our first page, it's all the x such that it's h of x, so it's the value of x, times its associated probability. So let's give you some examples here. A very common one that we have to calculate is, say, e to the x squared. So this is quite common. And for this, what we have is it's x and it's squared. So that's what our function h is in this case. It's the squared function. So in this, it's all the values of x. And we have our function, which is x squared. So it's x squared times its associated probability. Similarly, we could do x cubed. So what do you think it is in the chat? What do you think that this should be? What should I have written, kind of that term for the summation? Yep. Exactly. Yeah, it's because in this case our function is the cube function, so it's going to be x cubed times its associated probability. Nice. And you can keep going on. A, B, dot, dot, dot. Let's call this C. But I could do, say, x to the n. And same idea. It's x to the n times its associated probability. So I have, let me just make sure I number the pages here. I have number 3. So let's do an example. We're going to use basically this, but here is our question. A computer store has purchased 3 computers of a certain type at $500 apiece. So again, what I would do is, as you're for tests, this is important. There's information. We have 3 computers. There's 500 apiece. They will sell them for 1,000. So they sell them, and here they have purchased them. So they're down 500 apiece. So that's they're down 1,500, and hopefully they will sell them at 1,000 apiece. The manufacturer has agreed to repurchase any computers not sold after a specified period of time at $200 apiece. Okay, so there's repurchase, or basically it's like a buyback program. Based on the sales history, 10% of the time no computers are sold. 20% sell 1 computer, 30% of the time there's 2, and 40% they sell all 3 of them. And so they're not interested in what the expected number of sales they're going to have, which is, we could say, what we're going to do down here. We're going to let x be the random variable that denotes the number of computers sold. We're not interested in x per se. We're actually interested in this case, what is the computer store's expected profit? So in this case, we just have to remember that profit is equal to the revenue, all the money that you make, minus your costs. Again, because we have all this information here, it's probably something that we need to lay out a little better. So the first thing that I'm going to do is I'm going to write this as we need our PMF, or the probability mass function for our variable x. So in this case, write this out. There we go. Again, it's just organizing our information. So we have no computers 1, 2, and 3. So that's what the number, those values that x can be. So it's from 0, 1, 2, and 3. There's a 0.1 probability that they sell none. There's going to be a 0.2 probability that they sell 1. There's a 0.3 probability that they sell 2. And lastly, they sell all 3 computers with a probability of 0.4. So there's our probability mass function. So then what we have then is we want the store's computer expected profit. So H, and this is a capital X, is the profit function. Associated with selling X units or X computers. So again, we just kind of have to build now some of our functions. Again, this is part of modeling. We have the revenue minus the cost. Now the revenue is they're going to sell each computer for $1,000 a piece. So that's the money that they make from that. Well, they're going to sell it. So there's going to be $1,000 and for the number of computers that they sell. So that's 1,000 times X. Now for the cost, or what I'm going to say, there's two things. There's the price that they pay per computer, but also we have to also consider this repurchasing or this buyback program. So for the total cost, they purchased 3 computers at $500 a piece. Well, the cost then, well, that's 5 times 500. That's $1,500. So that's $1,500, and it does not depend on how many on X, because that's fixed. What they do have though is a buyback program. So they'll have that $1,500, but they will get back some of that cost. So that's $200. And this would be any of the remaining computers left over. So we don't need 200 times X, because X is the number of computers that they sold. We need the complement of that. We need to have 3 minus X. So that would be the number of unsold computers. So you can see that with this buyback program, it will reduce some of their cost. Oh, thank you. Yes. I said 5. I meant to say 3. Thank you. Okay, so what we can do then is let's simplify this a little better, or make it a little bit easier for us to handle. We have 1,500. Then we'll have minus 200 times 3. That gives me minus 600. And then the minus 200 and then over here I'll have the minus 200 and the minus X. That gives me plus 200X. Why wouldn't the 200 be positive? It will be when we simplify it. So distributing the negative here. I have the 1,000 and the 200, so that gives me 800X. And minus 1,500 plus 600, that gives me minus 900. I mean, in the initial brackets. No, it's not a cost. Okay, because the cost is what you're going to have to pay, right? So they had to pay the 1,500, but the manufacturer agreed to repurchase any computers. So that cost actually decreases because we're getting the money back. Does that help for that question then? Again, because we're getting that money back. This is the part of that repurchase program. But aren't we paying to get it back? No, 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 no. No, basically what this says is that the manufacturer has agreed to repurchase. So the computer store bought the 3 computers, and what the manufacturer has said is that if they have any leftover stock, they'll buy it back at $200 a piece. Yes, the manufacturer. So they'll repurchase it. Yep. And this can be quite common, things like books. So like a publisher will put out books, the bookstore will buy them, they'll try to sell as much as they can, and then the publisher will buy back any of the leftover stock, and that's what they're doing. If you had 200, 3 minus x. Yes, I think it should come out to the same answer. Yep. Yep. As long as you're getting 800x minus 900. So that's what we should have for our profit function. Then what we need to do is, now that we have our function, we have to calculate the expectation of that function. So hopefully I answered Francis's question. Okay, so by definition, here we go. We have all the values of x that it can take on. So it's h of little x times the probability of that value, x. And again, because I've written it up here as p of x, again, these means the same thing. So I could write this as h of 0 times the probability of 0 plus h at 1 times the probability of 1 plus h of 2 times the probability of 2. So again, what I can do here is I have 800 little x minus 900 times its associated probability. So I just still need this up here. So we have its 800 times 0 minus 900 times its probability, which is 0.1, plus 800 times 1 minus 900 times its associated probability, which is 0.2, plus 800 times 2 minus 900 times 0.3, and 800 times, so I have 2, and the last one is 3. And we can put this all into a calculator. And the final answer that you should get is 700. So this is the expected profit. And that's the end of that example. Now we do have some rules. Let's say over here we have number 5. Notice that this h of x is a linear function here. There's our slope, our x, and then there's our intercept, our y-intercept. So again, it's very common to see ax plus b. It's a linear form. So we see it often enough that we have a rule to handle something like that. So if we have the expectation of a linear form like ax plus b, that's equal to a times the expected value plus b. So what I've done down below is I started to show what we've been doing before. Again, this is just a proof. And what we've done here is, instead of having x in the bracket here, and this is where x would have been right through here, we've replaced it with ax plus b. So there's our function. So you can think of that as our h of x. And so over here, there's our h of x. Then the next thing that we can do is we are going to distribute to the p so that we have ax times the probability plus b times its probability. And then from there, what I can do is the summation can be applied to each term. So we can break it up. So there it is here and here. And then the next thing that I'm going to do is I will bring out this a. The a is a constant. It doesn't affect any of the calculation here because it's only depending on x. So I can bring that out. Plus, and same thing with the b, I can bring the b out. So what I'm left with here is I have the summation of x times its probability. So we know that that's the expected value. And over here, we have the summation over all the probabilities. And again, we know that the summation of all the probabilities should give 1. You can think of that as one of those conditions. This is one of the conditions of a PMF, that the sum of all the probabilities must give you 1. So again, just writing this out, a times the expected value plus b. And there we go. We've shown what we needed to do. From there, we have two cases. You could set b equal to 0 so that you just have ax equals, and the expected value then is a times the expected value. Or we could have it where a is set to 1, and so that you have the expected value plus b. So again, that would just be the expected value plus b. Okay, so we've talked about expected value, which is a measure of location. And that's what we were talking about. So remember from our lectures on descriptive statistics that we had measures of location, that's like the mean, or we can think of the expected value, that's a measure of location. But we also had measures of variability to describe how much the data is spread. Or you could also, the same idea applies for random variables. So here are the graphs of two random variables. I have x, so over here is the random variable x, and over here I have the random variable y. And what you can see here is that these look completely, well, these are different. It's very obvious. However, the expected value we can calculate over here. It's again, the values multiplied by their associated probabilities. So again, I have 4 times a half plus 5 times a half. So 4 plus 5 gives me 9 over 2. Same thing over here, I can calculate, so I've just drawn this little indicator here saying that this is the expected value. And over here, same thing, it's 4.5 as well. And we can see that that's the case because if I sum them up, it's 3 times a quarter, 4 times a quarter, plus 5 times a quarter, and 6 times a quarter. I get 3 plus 4 plus 5 plus 6, which gives me 18 over 4, which simplifies down that to 9 halves. So 9 halves is equal to 4.5. Same thing over here. So again, we have 2 random variables. They have the same expectation, but looking from this graph, they are not the same. So we need another way to describe them. And that's where we get this idea of variance, because this one is spread out more than this one. So we would say that this has more variance, that y has more variance than x. So I've just written that down here. Again, x and y may have the same expected value, but from the graphs it's clear that they're distributed differently. There are more possible values of y, and it is spread further out from the expected value, so therefore it should have what we call more variability. So using that idea of kind of the measure of how far all these values are from the expected value, this is what we came up with. Not myself, but this is what mathematicians came up with. It's the idea of variance, and it's the expected value of the square distance from the expected value. So we can write that as, they use V in our textbook. So it's the distance from the expected value squared, and we want that the expectation. So it's the expected value. So there's the distance between the expected value squared, and we need to take the expected value of that. The other way that we can express that is v of x. Instead of writing it as the e of x, sometimes they may write x minus mu. And again, same idea, mu is the expected value. Now we do have some rules of variance. And again, it's just to handle when the variable isn't just x, it's actually a function of x. So same idea again. We can have the variance of some function h of x. And what we can do is we can write all of x. And we'll replace x with h of x, so it's h of x minus the expected value of h of x. Oh, maybe I'll just be a little careful with my brackets. Times its probability. Now, if h of x is a linear form, like a linear function, a linear function of the random variable x, then the variance can be written as the variance of a, so I'm using a, which is a constant, and b is a constant, a squared times v of x. Now going back to our example with the two random variables, where I have, here's my distribution, here's my other distribution, I can use my formula that we had specified. Again, the variance is equal to the distance from the expected value, all squared. So we can pass that in. Here it is. I'm just working out the variance from here. Now this is just using the definition. So again, here's my values. So for this one, I have 4, that's my value, minus the expected value squared, and that's multiplied by its probability, plus 5 minus the expected value squared times by its probability. And if you calculate that, you get 1/4. Which are capital and which are not capital X's in the last formula? Okay. Just a moment. So like say here, this is a capital X. Same thing over here. Here's a capital X. Here is a capital X. Here is a small lowercase x. And same thing here. This is a lowercase x. Here is an uppercase x. Uppercase, lowercase. Same thing here. I'll just give you a moment to have a look at that. Okay. And moving on. So in this example here, so we did the variance then for one of the graphs here. So we found that the variance is 0.25. And over here, repeating the same calculation, we get 1.25. So again, we see that the variance of y is greater than the variance of x. Now I just wrote out a different symbol there. I got to be careful. I just want to mention that variance can also be written as, so when we had mu over here, some people will use sigma squared. Okay. Lastly, we had talked about standard deviation before. And if you want to calculate the standard deviation, well, all you have to do is take the square root of the variance. So that's important because they may ask for what a standard deviation is, and that's usually how we do it. It will calculate the variance and then we take the square root. Okay. Now we have a formula for variance. Now in the textbook they call it a shortcut formula. So the variance of it is, we have the variance x is equal to the expected value of x squared minus the expected value squared. So what we can do is I can show it that this is true by this following proof. So we start out by definition. We have, again, the distance from the expected value, and again, mu is the expected value. So it's x minus mu, and we're going to square that and take the expectation. Now using our definition, we can apply that to this. So that's, you can think of that as, this is now our function, that h of x. So here, you can think of it as h of x. Then the next thing that we can do is we expand this binomial. So expanding it, we get x squared minus 2 mu x plus mu squared, all multiplied by the probability. Then the next thing we can do is we distribute, or you can think of it as expand it. So now, and also applying the summation to each of these terms, what we get then is here's sigma x squared times its probability minus the sigma 2 mu x times its probability, and lastly the summation of mu squared times its probability. So this is by definition x squared. We had done that previously, just from our previous notes. Right through here, the expected value of x squared, there it is. Oops. And then we have here, again, the 2 mu can come out in front of the sigma. That doesn't affect the summation. So all that we're concerned about is x times its probability. So that's mu, or the expected value if you prefer. And lastly, over here, we have the mu is brought out in front of the sigma. And this has to sum up because it equals 1. Again, condition of a PDF, PMF. With the simplification, we get the expected value of x squared minus 2 mu squared plus mu squared, which leaves me with the expected value of x squared minus mu, or you can rewrite that mu squared, this mu squared, as the expected value squared. Okay. And lastly, here is an example which we'll use to summarize all that we've covered in today's lecture. So, an appliance dealer sells 3 different models of upright freezers having 13.5, 15.9, and 19.9 cubic feet of storage space, respectively. What they're going to do is let x be the random variable of the storage space amount purchased by the next customer to buy a freezer. So x has this PMF, or this probability mass function. So we have we have x. So 13.5 cubic feet, there's a 0.2 probability associated with that. 15.9 cubic feet has 0.5, and 19.1 has 0.3. Okay, so, and this is an exercise from the textbook. So, computing this, all I need is just this PMF. So here we go, the expected value. I need x value times its probability. So it's 13.5 times 0.2 plus 15.9 times 0.5 plus 19.1 times 0.3. And you can punch this into the calculator. So 13.5 times 2, 15.9. So we get 16.38. They want us to calculate the expected value of x squared. So that is the x value squared. So 13.5 squared times 0.2 plus 15.9 squared times 0.5 plus 19.1 squared times 0.3. And if we punch that into the calculator, what we get is 272.298. And they want us to calculate the variance of x. So what we can do is use that formula that we had. So it's the expected value of x squared minus the expected value all squared. So writing that down. Which is kind of nice because that's what we calculated. So I'll have 272.298 minus 16.38 squared, and that yields 3.9936. Okay, the next thing is if the price of a freezer having capacity x cubic feet is 25x minus 8.5, what is the expected price paid by the next customer by the freezer? So what they're asking for is what's the expected value of 25x minus 8.5? And using our rules, we can actually apply that. So I get 25e of x minus 8.5. So I get 25 times the expected value, which is 16.38. And what we get then is $401. So that's what the expected price is paid by the customer to buy a freezer. Okay. For the variance, I have 25x minus 8.5. Using our rule, the variance is ax plus b is equal just to a squared times the variance. Well, that's then 25 squared times the variance, x. And we calculated the variance of x, so that is 3.9936. And putting that into a calculator, you get $2,496, which is the variance. And lastly, if you want to do this one, just as an exercise, what you'll get, if you suppose that the rated capacity of the freezer is x and the actual capacity is this function here, h of x, what is the expected actual capacity of the freezer purchased by the next customer? Well, it's the expected value of this. And yes. So what I have here is this function, h of x, times its probability. So again, what I get is like 13.5 minus 0.01 times 13.5 squared times associated probability 0.2 plus 15.9 minus 0.01 times 15.9 squared times its associated probability. And lastly, 19.1 minus 0.01 times its associated probability. And so if I put that into a calculator, what I get is 14.0098 feet cubed. And that's the expected amount of space in the next one. What will we cover in the next lesson after the midterm? So I would expect in the next lecture, we're going to cover section 3.4. Okay, is there any questions before we sign off for today? Okay, thank you everyone for tuning in. I wish you good luck on Thursday, and I will see you then at 8 o'clock. Could you post? I don't have any previous year's midterms. I'm sorry. What I would say is make sure to look at the quiz and the questions that we've done from the assignment, as well as lecture notes, and that will be reflective of what we will be doing. I would also say this is going to be an open book, but I would say have all your notes prepared, and perhaps even consider having a formula sheet ready so that for quick reference. Okay, take care everyone.